Okay, so we can start. Hello, my name is Aleksandr Tavgen. I'm working as software architect in Playtech and mostly related with research and design project and made a lot of things in our company more effective. And additionally, I also develop a high-performance time series engine, which we plan to open source, I guess, this autumn. And this is quite summary based also on development on this project. So actually it's quite a large topic, and I want to scratch to show just one aspect of it. And anyway, even this one aspect is quite long, but I'm trying to give information as short as I can. So let's start. What is concurrency and parallelism? Because actually a part of this talk was influenced by Nikita Salnikov, some previous speeches where he asked, why do you need Reactive if you are not a Netflix? Why do you need? You can work in a standard paradigm. And actually there is a concurrency and parallelism which are often mixed together, but actually the problem for concurrency and parallelism actual for both of them. Shortly we can see the differences as we have one ball and two queues of kittens, and in concurrency it means that only one kitten at a time can eat from one bowl. In parallel way there is two bowls, and at a time two kittens could eat food. But what is missing on this picture, here is missing a cat owner, and a cat owner is an operation system which reschedule kittens based on the strategy or on behalf. Everyone, I guess, knows the differences between process and thread. And actually this picture is the part of the structure which named process descriptor, and it is associated with every process or thread. So actually the differences between them that threads can share the address space of process or some resources such as file descriptors and so on and so on. And actually for the kernel there is no differences between the process and the thread. They have exactly the same data structure. Only threads are grouped in a thread, in a specific kernel group, thread group. And actually the shared resources is what makes pain for us. Here is just simple picture where we have, for example, some shared data, and we have some threads which concurrently have access to this data, have some reads, have some writes. What problem could be seen here? For example, if two or more agent threads want to change the same shared data, then you can see wrong results. For example, we can imagine that this is some web server which received some request, and for every request, counter about the total request should be increased. And you can see that here we can receive a wrong result. So instead of 19, we will have 18. And usually it means that you have some wrong ordering of your executions. Another part which were invented to cope with these problems is a different mechanism for synchronizing state. And for example, most known is like lock. It means that when one thread acquires some resources, it locked it, and if another thread wants to access the same resource, it should wait. There is another so-called synchronization primitive idioms like barriers. It means that everything that what reordered should be finished before this barrier. And actually there is a set of algorithms which could be lock-free, like compare and set, where we read, we modify and compare whether the initial value was changed or not. If it was, then we repeat the computation. So it has some performance implications in that case. And there is another problem which called deadlock. if different threads want to acquire resources in different order, they can finish in situation where they mutually blocked by waiting the lock. So actually, in theory, you can have a beautiful picture that you have a lot of threads which executes in concurrent and parallel way, but in practice, usually it looks like this. And let's go deeper and try to understand why we have problems in a so-called low level, in the hardware level. The main problem is a gap what we have between processor and memory. I mean a speed gap, performance gap. And you can see that this gap is constantly increasing, because for the processors we can apply different optimization techniques. We can apply some caches, we can bring data more local to core, we can have some pipelining and micro instructions, but the memory performance increased in a quite slower pace. And if we take some modern processor internals, then usually it has from 1 to multiple cores, which is like a separate small processor, separate execution unit, which has some own local memory, but they also sit on so-called L3 cache, which is shared among them. And then we have another shared mutable state. Actually, there is a fallacy amongst a lot of developers, because some of us think that source of truth is memory. So we can have, for example, some cache flashes and so on and so on. But no, the actual source of truth is cache, because all the operation goes through the cache controller. So it means that all your writes to memory or reads are controlled by a cache controller. And here you can see the actual speeds of accessing memory. So the fastest one is processor registers, which is close as possible to the core. There is another thing like memory ordering buffers. This is already core internals, and we'll speak a bit later. And we can see that the farther from the cores we have our memory units, the more time we need just to access to them. And again, all the data goes through all levels of cache. And because we have a shared L3 cache, we need to have some cache coherence protocol, which means that it should synchronize or make a consistent memory which is shared among different L1, L2 cache, which is local to different cores. So this is actually a picture of one core internals. A lot of elements, quite complex, but main things is that there is a pipeline like in a factory, where your machine instructions are split by so-called micro instructions. Because, for example, if you have some operation, for example, I want to add some register with some memory cell, it means that it could be splitted. For example, access to memory, waiting for receiving some information. And in that case, another operation could be also executed. It means that in a core level, a lot of operations are unordered. So it means that the order is not preserved. And there is different caches for data and instructions. Again, it's made for the optimization of pipeline, because pipeline always takes the data from L1 cache and data from here one. Another main important thing is that there is an internal so-called virtual registers, because there is no one-to-one mapping. And all the storing and loading operation are going through the queue. So that's how the processor preserves the order, how processor core can finish an ordered operation. And the main problem is that all data that are in L1, L2 cache are inclusive in L3 cache too. It means that if you have some application, some threads working on some shared data structure, and this data structure situated in L3 cache, then you will have a problem. Okay, so there is a special protocol which called cache coherence protocol, and here, as you can see, all the access to the memory goes through the caches, and there is some different status of cache lines. For example, modified and means dirty should be, for example, should be written to the main memory. Exclusives, that this, for example, is located only on this on one core. Shared, that it could be shared between different cores, and so on and so on. So it means for different processor models it has some differences, but it means that if you want to make some synchronization, or you want to finish all reordering operations, then you need to synchronize cache as well. You need to that your memory lines should be consistent. And here is how it looks like. Because in a processor there is a special sets of instructions which called memory barriers or fence instructions, and there is a different variations of that. For example, for read and write operation, but in general it means that all the operations which are executed on core pipelines should be finished. All unordered operations should be finished. It means that processor just waits for the all operation to be finished. After that, cache coherence protocol is executed, so we make consistent our shared state, and as a result, all the pipelines, which again give for us performance improvements, are flushed. And there is another side of coin, memory model. So in the background picture, you can see how it looks like, for example, mapping virtual addresses to the real physical ones. Because again, if you want to be hardware independent, it means that your program, your application, your process could run in any address space. So there is a special mechanism for resolving such addresses from virtual addresses to physical one, and usually it needs to it needs access, for example, to main memory, which is expensive, and it needs some computation to combine the final address. Even with the data which is presented on L1 cache, you will need to lost 16 cycles of processor for every address resolving. Without caching, it would be almost impossible to operate on current speed. And there is another cache for that, which called translation leukocyte buffer, which means that if you resolve some so-called like pages in memory, so the partially or fully your part of this address is stored in the cache. And there is even some attacks which is use this interesting approach. For example, if you even want to access some protected memory, you can measure the time of segfault, for example, and it means that if this address were already accessed by someone else, then it means that it is in a TLB cache. So, what does it mean? Everything. Our machines, our computers can execute a lot of processes, a lot of programs, a lot of applications in concurrent and parallel way. Again, their operation system offers like an interface for accessing the file system, for some network calls, etc., etc. And for every such kind of operation, for changing, for example, one process to another one, or to make a system call to a kernel level, you need to make some context switch. And context switch means that you need to store all your context information, your process registers, all your pointers to codes, some paging information. Again, it could, and usually it flushes core pipelines, and it is expensive because you need to store some context from old process or thread, restore one, and it takes time, and it's even worse. Because if we take the common process switch, then there is actually two steps. We need to switch, in the case of process, like a page global directory where we are resolving our addresses, and we save all our context from current process thread and restore another one. But actually, it's quite a complex logic, and it takes about 4 or 5 pages in description in the standard Linux kernels. But the true cost of context switches or syscalls is much larger, because if you have a caching validations, if you have a core pipeline flushing, it means that the next processes which get the execution time will suffer from the empty caches, and it needs some time just to refill all this execution context. And actually, as you can see, the true cost of context switch and syscall has a long-lasting effect. And again, if you have a lot of context switches, you usually have a degrading performance in an exponential way. And this is real, actually, information from our production system, automated monitoring. And here, actually, some units of work which we execute. And here, it's quite small, but you can see that common execution time is like 40 milliseconds, 69, 46, 56. So it's between 40 and 60. And here, I just added some work to the kernel, and you can see that in case of increased kernel rescheduling, we have overall time increasing, and we have some separate queries have execution time up to 500, 1000 milliseconds. And again, the constant time to DB is quite uniform, some 40, 50 milliseconds. And let's take like a closer look. So actually, here, this trace, 79 seconds, is DB call, which is quite constant. Here we can see some missing values. This means that in that moment, this thread was scheduled by kernel. And here, it again received the computing resources, and you can see that this execution takes almost 50 milliseconds. In normal case, it takes from 1 to 3 milliseconds. It is it is a computational memory intensive piece of work. So that's why empty caches after switching has so drastic impact on performance. And if we make some traces on kernel level, this is like a Python VM with thread-based execution. We can see a lot of mutex operation, the same logs, and this is depends on a global interpretation log of Python. But here, we can see a lot of get times of the day calls. Actually, get time of the day call is one of the 4 functions that is mapped in a user address space. It means that if you want to call get time of the day, you do not need to have a switch to a kernel level. We can think that, okay, get time of the day, what? So some strange function, we just probably need to know what time is it now, but actually not. This function has this mapping with a purpose, because this is a global clock on an operation system level, and if you have a virtual machines which have some internal operations with memory, so you need to have a synchronization with the operation system. And here is quite also interesting moment when input-output operation from the disk the data memory map means that when kernel receives the data from the disk, it will write it directly into user space, and process also can work without a context switch. So, small summary. We know that synchronization cost and the core pipelines flushing is quite expensive, because it has a long-lasting effect and affects other processes which is run in the system. Again, thread structure is quite expensive. You actually saw there is a huge memory structure with different stacks for threads and for kernel level. And the most important, that overhead of managing a large amount of threads is quite high, and it increases in a non-linear fashion. Why do we need so many threads? Because actually, thread is quite this is a primitive which is supported by operation system. It's very cheap to implement, for example, on a virtual machine level, on a Python or for a Java. And for example, if we take some execution paths of our applications, and usually we have some database calls, we probably have some network calls to another services, and if we are using blocking by nature drivers, it means that a lot of our threads just in a waiting state, waiting for response from these calls. And for example, this is common models for a lot of web servers, when every new incoming HTTP request is associated with some thread, new or from the pool. And there is a classic problem called 10,000 connection problem. It means that if you have a roughly say 10,000 threads, then it's probably infeasible for a normal machine to cope with such amount of threads. And actually it means that also your code is more waiting than working. Because if, for example, you open some book about how to scale application and so on, so then probably first recommendation is to add some application instances. Why? Because usually a DB can handle more load that your application can provide, because optimized DB is working in an asynchronous way with a quite complex mechanism, again, about the managing own state. And for a lot of operation, for a lot of application with blocking synchronous drivers, this is true. So thread creating, and operating is expensive for everybody, even for other processes. Threads which is blocked by synchronous call can be rescheduled by OS kernel. And if you have a lot of threads which is blocked, it means that you constantly will have a context switches with all this pain inside. And this was like the intro, which like introduced how the modern hardware, how the modern processor is working. And here are some recipes how we can avoid a pain related to that. And functional approach usually associated with avoided shared mutable state. So we have some state which we share between the so-called object, because there is no object. There is functional compositions, which means that if we have a functions in without a side effect, so-called pure function, then we need to combine them in high order functions, which in turn is also pure, has no side effects. And it means that you can combine all these function or execution paths before the actual execution, so-called lazy execution. And pattern matching is actually, it means that defines the different, in a shortly explained, it defines the different ways of your logic, depends on incoming data in your functions. So the main problem with object-oriented programming is that you have you model something with an object which you have, for example, some fields, private, so you encapsulate some state in your objects. You have some interface which can change the internals of your object, and this object invariant can be broken. For example, if in process of changing the state by some outer call, the operation system reschedule your thread, and another entity want to access to the same object. And the most important, the semantics of object-oriented programming is oriented on nouns. So like me, which has some method walk2, take some object as a store or shop, open, and so you can see sometimes it's even quite verbose. So the functional programming approach is oriented on functional composition, when you can split your execution paths on some simple blocks, and then if this simple blocks has no side effect, it means that if you constantly have something in your input, you will have something in your output. The same type in, same type out. So you have no exceptions and you change nothing. And again, if you have no such side effect, you can compose all this in some more high level functions. And here semantics is more oriented on verbs. Yes, so you have some composition of walk, open, store, add the basket plus milk. And again, some of the execution paths is easier to model in this way. And here is like the execution. If we have functions which mapped arguments and some return values, then we can combine them before actual computation is started. Because, and actually we can combine it in a more complex way. And it means that we define our pipelines or execution paths in some declarative way, and it means that runtime has more freedom to optimization, because if a function return always the same value on same input, we could cache it. So we even do not need to create every time the same computation on these functions. So it means that runtime has more freedom to optimize your work. So common idioms, everybody, I guess, heard about that. Map, filter, reduce. So actually, functional approach is influenced on a lot of some frameworks, map, reduce, Hadoop, or some different language stacks. You can see those elements in Java, in JavaScript, in Python. And that was about some small intro about functional. And here is, I want to introduce some main areas of reactive programming. This topic is not new actually, because a lot of ideas were like presented and invented some 40, 50 years ago. But this reactive manifest is talking not only about writing an application, but it's probably mostly about how we design the system, about the architecture, or about some implementation in details. So like system should be responsive, so you always, if you have some input, you have some guarantees to receive some response. It's message driven. It means that there is no blocking calls, there is no remote procedures execution. Every information is exchanged by passing messages. Resilient means that you have some logic where you have some abnormal situation, and elastic, it means that it can cope with the increased load, so it have some backpressure mechanism, such a buffer, or for example, you can just simple drop. And reactive approach or working on some green threads is actually implemented, have some implementation. So this is like a actors model, which is quite old and was introduced by Erlang, so Elixir, Scala, Akka. There is a communication sequential process where you have like the first-class citizen communication channels, and we can meet this model in Go. Kotlin coroutines, same way, and Java reactive interfaces, which were introduced like in some standardized way in Java 9, and has also different implementation. So actually we have like two different paradigms or approach. One is functional, which is point to building software by composition of some execution paths, avoiding some shared mutable state. And another one is reactive, asynchronous programming paradigm, where you operating on data streams and propagating changes among them. So actually they are quite complementary to each other, and that's why sometimes it's named like functional reactive approach. And what is the main goal about all this topic? The main goal is that this could make more effective usage of modern multi-core CPUs or threads which is competing for resources of those cores. So actually, it looks like Haskell sometimes. Yeah, this is Java, but here is a quite interesting thing that you can define your execution paths in a reactive way, even working with a database. So here is implementation of breadth search, which means that if you have a graph of metrics, so it began to make a recursive call for every incoming data. So you can see this classic way where we have some list, we check first one, make some request, asynchronous, and based on results we compose and call itself and merge results. So before actual computation, there we define like a pipeline. And actually, when this code is running, we switch DB in so-called streaming mode. So the new requests continuously are going to the DB, and after some moment, DB begin to streaming the different amount of data, and you have a defined pipeline how to propagate those changes. The main actually differences between so-called Java 8 model and reactive, that first of all, Java streams is about the operation on your collections. It's not about the executional path, but the main paradigm behind this is like iterating. You have some consumers. You ask about a new data after you processed your piece of data, and you are going like that. The reactive one is oriented on a push model. So again, wherever you have a data, it will push and propagate it through the executional path instead of iteration. And the main problem with blocking threads is just if you have some limited amount of threads, you have some streams of data which want, for example, make some external call or have some blocking operation, then every this operation blocks this thread. It means that it will be rescheduled, and you have like two ways, like I need to add more and more threads and suffer from that, or you can have share those expensive resources as a threads and process on some lightweight construct, like functional composition of your execution path. And non-blocking processing means that if you have like small amount of threads, usually mapped one thread, one core, and all your requests putting in some queue, you have some DB or some call, and you have like callback attached. We can compare, for example, I'm sitting in a bar. If we as a company, for example, and if we want to take a beer, the one way we need to go by ourselves and wait in a queue while the barman give us some beer for us, or we can call a waiter, give our, for example, we want beer, and call back number of our, for example, my name. So the waiter knows who needs to receive this beer, and I can to send all this requests in a more effective way. So let's test. This is real test which I made on our work. So it consists of more than 2,500 units of work. Every unit of work is requesting DB, taking some data point, and computation work. Computation quite expensive. You need some memory requests. You have some comparing, and so on and so on. They scheduled once in a minute. So once in a minute we check our, for example, metrics. And classical execution on 8-thread pool with blocking driver takes approximately 30-35 seconds in dedicated server in production. So let's map the same amounts of work on, for example, on threads and our reactive pool. So here is more than 2,500 threads start. You can see in the right every minute pieces of execution. They are non-uniform, and which is most important, they have some of them quite significant amount have 5 sec timeouts. So the response will not be received within 5 seconds, so you drop it. And you can see even here that the amount of threads from 2,500 dropped to 2,100. You can see here disturbances of your CPU. What all this so pattern means context switches, because if you some drivers is blocking, then operation system decided to reschedule it. So all this kind of thing is some switches or overhead from the managing and operating all these amounts of threads. And you can see memory picture which has spikes, which has some garbage collection executed and goes sometimes up to more than 1 gigabyte. Here is 8 threads with a non-blocking execution, input-output. We can see here, first of all, quite uniform scheduling of work. So it's quite uniform. It takes 10 seconds. We can see here that we have no disturbances at all. We have some spikes on our scheduled work, and which is most important, we can see that this code is hotspotted and optimized. So within a time, it became less and less expensive. And we can see here our memory picture. So it's almost constant around some 600 megabytes. So more effective for almost on 40% without some significant garbage collection time. So one more time. Here you can see these disturbances. And what is most important it's not about how your application behaves, but all these spikes, all these switches, flushes caches and affect all other things which operates in the same machine. It means that if you have such picture on your application, it means that other processes which operates in the same machine has the problem with performance as well. And here is like different picture. So one thread, one execution path, classical way, and if you have a lot of threads, you will have quite problems on the performance side. One thread, many execution paths. And as I told, usually if you want to scale your application, you have some recipes. For example, try to increase amount of application instances. Here, before this spike, you can see this is our production DB time series, which has every second some 10, even more, some around 200,000 writes. It has in parallel way every time execution in our monitoring system, some Graphanas, etc., etc. So as you can see, a lot of different systems working with this, and they cannot load this DB in a full way. So here is like some tests which I made, or creating some models. And you can see that one instance working in a reactive way can load up the DB up to 100%. So there is even almost no usage idle. So it means that it's possible to have the increased effectiveness, increased performance. It means that you can have a service binded with some storage with your DB, which work in an effective way. Your code is not waiting more than working. You can think that, okay, well, no, it doesn't matter. We have some virtual machine, we have some additional power on it. But again, all this kind of stuff is actually have a very it has the financial value. It means that if you have some high performance, high throughput operations, then switching from, I don't know, 10 application working in a blocking mode to 1, 2 is a quite huge it's quite huge benefit from even from the financial side. So actually I've just scratched one piece why the functional composition and reactive approach can help utilize our modern processors, our modern operation system. But actually reactive is just more than asynchronous execution and non-blocking processing, because there is a quite advanced time scheduling and flexible. What does it mean? For example, if we have units of work which should be executed once in 10 seconds, another one once in a minute, another one once in a day, maybe some BI once in some hours. So it's very hard in a natural way to work with all those kind of units of work, because you will probably have some time sleep and so on and so on. So reactive engine give you possibility to precisely schedule execution of your units of work. Again, there is a backpressure control which is quite efficient. For example, you can receive data in a more faster way than your current application can cope with, and you can create a logic for that. So it means that if you have some load spikes, your application will not crash with some out of memory or decrease in performance in a very inefficient way. And there is a quite advanced also logic where you can define how you behave receiving some errors. Actually, the term coined in Java Reactive Revolution is made by George Long. It's one of the Spring developer advocates. And right now, there is a huge amount of different drivers for example, for some InfluxDB, Neo, CoachDB. There is implementation of Reactive GDBC, and community is working intensively on a common implementation of GDBC in reactive way. Spring 5, the main advantage of Spring 5 is a native way of working with reactive primitive like a web flux, so you can have your Spring application working in a reactive way, and you just can test and try, and you will see the quite significant differences. And there is an active community working on all this kind of stuff. Even in Java, there is a different implementation of reactive stacks, like RxJava, which was developed by Netflix and supported a lot of by Android operation system, and Reactor, which is supported by Spring. Vertex is quite old stuff. So actually they are also quite interconnectable, so it's quite easy to, they have the common interfaces, and you can easily work changing them. And for some, even if you want to have some more information about the internals or how modern systems work, is some books which I could recommend. It's Understanding the Linux Kernel, so you can find some different specific questions related probably to some specific pieces of work, how network drivers work, how, for example, some asynchronous processes. Optimizing Java, it's quite classical thing, which reveals some internals of JVM and also put attention on some JVM internals. Amazing book, 7 concurrency models in 7 weeks from pragmatic programmers. It's quite cool series, which actually there is a lot of brilliant things related with this pragmatic bookshelf. And learning Haskell. Yeah, sometimes, yeah, it's everybody hates Haskell, but you can, for example, just making some simple intro in that language. It's easiest way to change the paradigm of working with your code.
One thing to add from my side, there's a free online book on learning Haskell called Learning Haskell for Great Good. Cannot recommend enough, very good one, and this is maybe the best place to start with Haskell.
And another book, Simon Marlowe, about the concurrent programming in Haskell.
So you know, there is a guy who knows Haskell. So actually, yeah, it's a good way to just.
Guys who know the book. I was playing Haskell for 2 months.
So yeah, this is actually, it was quite a deep topic, because it's not possible to push everything even in just one aspect in 45 minutes. But actually, the same approach is suitable for architecture, but for more high level, where you can combine your services in some functional way. You can have pattern matching instead of contracts, because, for example, if you have some queue messaging, then within some years you have, I don't know, contract version 25. So this is like a problem. So this approach also works on some distributed manner as well, because it can simplify some problems with distributed systems, such, for example, eventual consistency. And my HRs asked me to put this as well. Yeah, we are hiring, and if someone are looking for a job, so you can also speak with us as well. So any questions?
One brief man. In what processes do you use this reactive style, and how easy it is to mix this together, reactive and non-reactive code?
Yes, there is actually everything is nice if you have some fancy reactive drivers which created by community. Everything is okay. It's quite easy. The main problem is actually two sides. One, sometimes it's not trivial to break your execution path or your logic on a functional composition. Sometimes you need to write in Java like a Haskell. This is like one point. Another point is, yes, if you have blocking drivers, then you have like two options. For example, in some reactive schedulers, you have some schedulers I/O, where it has separated thread pools for executing blocking queries. But again, you will face the problem if you have too much of them. Then you will see the blocks on this side. Another possibility is to wrap them in a futures, or in some, or make some completable future chain, which is also not so trivial in case of some complex logic. So Yes, there is a problem migrating from the, for example, so-called old application. But sometimes if you work in some, if you have a quite small microservices already built, then it's quite easier, for example, to switch from the asynchronous HTTP call server to asynchronous one, and then, for example, test some drivers. Again, there is implementation of Reactive JDBC, but there is no one common so-called standard implementations of Reactive JDBC. But community says that probably this year we already when you have a lot of quite large community and a lot of interest in the backward compatibility, then it's probably the main problem is not the technical one. It's just about how to communicate or how to make agree between all the parties.
One question from my side. You know that computation power is cheap and programmer time is expensive. And also another component to this problem is that there is a lot of tools are available at your disposal which are implemented in object-oriented paradigm, right?
Yeah.
And then there are not, like some of them are, like Spring 5 you mentioned that you can totally run with in reactive paradigm, but most of the tools that compose your modern stack just do not support it. And then if you choose this reactive way, then you're limited to only the toolset that supports it. So like what kind of scale has it be to actually justify the decision? So coming back to Nikita's comment on Netflix, obviously it makes sense for Netflix because they introduced it for Spring, right? So what scale of your business does it have to be for such a decision to start making sense?
Actually, it's a good question because if you operate on some clouds, then you probably have some numbers. But for example, in Playtech, we have our own data centers, we have our own capacity management. So actually, we have a so-called cloud management, and actually there is a so there is a numbers. Always there is a numbers. For if you want to cope with some, for example, I don't know, 20, 30 concurrent requests in transactional sense. So your, for example, infrastructure environment could start from some millions, some $3-4 million of dollars. Again, there is a quite differences if you, well, you're small, yeah, it doesn't matter. Computational power is cheap. But when you step into some high load area, then even reducing from 10 instances to 2, which, for example, requires some serious computational power, within a month, within a year, can bring you some great benefits. For example, I can also tell why we also develop such kind of engine. Because current commercial solution is built upon some old paradigm. For example, Hadoop MapReduce, they store all this amount of data, they make some MapReduce work, and they requires for operation without license, without expensive license, minimum for operation on 200,000 metrics, 32 virtual CPUs and 64 gigabytes of RAM. If you need more than 200,000, then you need another the same kind of machine. Which
so it scales by 64 gigs of RAM. Basically.
For example, some solutions, yeah. So again, if you have solution which you can split actually stream processing, you don't need some complex server because again you do not have so much blocking requests, so you don't need to scale vertical. You can split on some small instances which could run and work in parallel.
But at the same time, the server costs 20K only, and then amount of time invested into your own solution costs.
No, I mean that, for example, I mean if you have even I'm just the amount of request hundreds of thousands per minute. It's just on some markets. If you just for example some Asia, if you go in another process, another process. So even some reducing some infrastructure needness on some 30-40%. If you operation on millions, it's quite high. And again, if you splitting your monoliths that everybody hates, or for example, if you're building your system starting from small units of work, some small services, you can switch some pieces of partial work quite easy, because you don't need to have a cascading changes on all your stack.
Thank you so much.
Thank you.